Well, good morning, Precock. Here's the do now for you. You're going to describe in words your prediction. What would happen if Pinky were to walk further to the right across the graph? What would happen to the height of the graph as Pinky walks further to the right? Oh, I was going to wait until you figured out what your guess is. Okay, well, the answer is this graph totally doesn't look like maybe what you thought. So as Pinky goes further to the right, woo, and as you go off to the edge of the graph, if you go far enough, the height goes to 0. And if you want to see the whole entire graph, I've got a link here to this equation in Desmos. And you can see the equation right there is weird. But see if we can zoom out. So after that first initial bump up and then down, and then it kind of settles in on 0 as it goes out there to like infinity. I want to keep going. I mean, 500 is far enough, right? So that is our do now. The learning target for today is we're going to continue looking at limit notation, this time to describe a graph's end behavior, left and right end. What is going on out there? So we know that a limit is a y value. It's the height, the function value. So a limit is the y value that a function approaches as an input, or the x coordinate approaches some x value. And so in some ways, a limit is similar to an asymptote. You remember from previous math courses, or maybe from me mentioning it the other day, that an asymptote is a line. It's not actually part of the graph, but it's like a reference line that a graph approaches but never actually arrives at. And so here's the graph that has this pink dotted line represents a horizontal asymptote, and the two green dotted lines represent vertical asymptotes. The graph just doesn't exist at those points. The curve gets closer and closer and closer to the green dotted line as you go up here. If you went to the left, I don't know why we're going backwards. The further left you go, the curve gets closer and closer to the pink dotted line. Never actually arrives there. It doesn't cross it. It doesn't touch it. And the same thing in all these other places. So the graph approaches the value of the asymptote. If I take my graph walker and let them move from left to right, the graph walker approaches an x value of -2, but never actually gets there, right? And so an asymptote is just an idea that says, hey, you know what, we're approaching something, we never get there. That's fine. We need some way to describe it, to understand it, to deal with it. All right. So a limit is the same in the sense that graphs do not actually need to arrive at a certain point in order to have a limit. So the difference, I mean, there's a number of differences. The key one is with an asymptote, a graph can't arrive at that point. If it did, then it wouldn't actually be an asymptote. And with the limit, the graph could actually arrive at that point. It's a moot point. It could arrive, it could not arrive. It doesn't make any difference whether it does or doesn't. So the limit notation, it's all the same. So we're going to look at what we've seen before, limit notation. So limit notation, I'm going to scroll back up in a minute. Limit notation is similar to an asymptote in some regards, just the limit aspect, because it's approaching. And so the notation underneath here in green, x approaches positive infinity, or it might be negative infinity. Those are our two ends, the right end of the graph on the x-axis. The right end is going to be positive infinity. The left end would be negative infinity. And in the blue circle here, this is what is describing what the function does, the height, the y coordinate. What does the function approach as that x coordinate moves closer to whichever end we're looking at? So our job is to fill in this height. What height is the graph heading towards the left end and the right end? Right? So we can use this for end behavior. So here are a couple of examples. Here's the first graph. So I got our pirate ship here. So this graph does, some weird stuff in the middle. We're not concerned with what happens in the middle right now. Right now, we're concerned with what happens at the ends. So the blue box up here, the limit of the function as x approaches positive infinity. that means we are going towards the right side of the graph. Whoops, I changed the color of the boat. That's not right. Draw. Oh my goodness, I want to draw a line. The right end of the graph over here is heading towards a height of 2. And it seems like maybe that's an asymptote. Okay, whether it is an asymptote or isn't an asymptote really is not relevant. The point is, as my pirate boat sails across the graph, if it kept going and kept going and kept going, it sure seems like it's leveling off at a height of 2. So that is my right end behavior. And then for the left end behavior, the limit down here in the green box, the limit of the function as x approaches negative infinity. So it's going to be the left end of the graph over here. If I take my magical graph sailing pirate ship and go towards the left, so pirate ships have different rules than graph walkers. Graph walkers can't do this. Pirate ships do whatever they want. They're pirates. Scar. That might be taking your analogy too far. Anyways, you go off the left end of the graph. It sure seems like this graph is leveling off at a height of 0. I was waiting for you to say it first. And if, I probably should have used a highlighter. If I get my arrows out of the way here, we can actually see what this is looking like. Whatever. All right. So here's another example. Different graph. Again, discontinuous there in the middle. It's not attached. You got 2 branches. They're doing like who knows what. But in the middle, if Princess Buttercup sent our 2 dread pirates to the middle to find out what's going on, wow, they'd be doing opposite things here. But we're looking at the ends. So up here in the blue box, the limit of the function as x approaches positive infinity. So I'm going to look at the right end of the graph. Let's use a highlighter so I can still see that graph. And in this case, the height of the graph as it leaves to the right side of the graph seems like it is leveling off at -3. And graphs do not always level off. I know these first 2 examples, they look like they're leveling off. It's just because I wanted some good examples where we can see what's going on. That is not always a thing that happens. Graphs don't always level off, so don't expect that. Here's our next question here. The green box, the limit of the function as x approaches negative infinity. And that tells us we're going to head off to the left edge of the graph. And as you head off the left side of the graph over there, grab this pirate ship. Shoo. Whoops, I lost it. Yeah, it's going to sail off the edge of the graph there towards the left. Seems like it is leveling off at a height of +3. So with limits, if we're doing end behavior, we read end behavior opposite of the way that we were using limits yesterday. Yesterday, we had our pirate ship starting at the edges of the graph, sailing toward some x value in the center of the graph, I mean, somewhere in the center of the graph. And that was fine. We'll still be doing that today. But with end behavior, we are heading towards the edges of the graph. So you can start your boat in the middle. It doesn't matter anything that's going on in the center, whether the graph's attached, not attached, doesn't make any difference. Positive infinity means you just sail your boat off the right edge of the graph. What height are you heading towards? And left end behavior, the negative infinity means you're going to sail your boat towards the left edge of the graph and see what height you are heading towards. So there's really not a way to read the graph with limit notation. You follow what the directions are. It's not you always move left to right or always right to left or always this or always that. You do what it says. If it says x approaches positive infinity, that means your boat is sailing towards positive infinity. If it says x is approaching negative infinity, that means your boat is going towards negative infinity. Okay, last example. Actually, not last example. Sorry, next example. So on the right end, height of 1. The left end is a height of 5. My colors here. +5 for that one, +1 for this one. And maybe we'll make this one the last example. So here we got a graph that is not leveling off. And as I sail towards the right end, let's do the blue one first. The right end seems to be going down off the bottom of the graph. The left end heading up from the perspective of that's the way I'm going. If my boat is going towards negative infinity, it's sailing this direction, that is going up, right? So with limits, we don't have to read from left to right. So if we were describing this like in terms of intervals, this green thing, we would have to read from left to right, and we'd say, well, that's a decreasing interval. Correct. This is not interval notation. And so when the limit here points us towards negative infinity, that means our boat is sailing off towards the left side of the graph. So we're actually reading from right to left. And in that case, it's increasing going up to positive infinity. So I know there's like lots of different ways we have to look at graphs and think about graphs and describe graphs. And switching back and forth from one type of notation to a different type of notation means we have to change our thinking, and that's hard to keep track of, which is why I always encourage you to take notes. You got to write this stuff down. If you are not the kind of person that just says, I memorized it, then writing notes is going to be a fabulous way to keep track of this stuff, because interval notation, we read graphs one way, maximum and minimums, we read graphs a different way, limit notation, we read graphs a different way. There's a lot of stuff to keep track of.